we know that when we are taking a sample from the population, the sample to sample, the mean value or the sample proportion will change. But when we are estimating the population mean or population proportion with a sample mean or sample proportion with a point estimate, it will not give any uncertainty, right? Because sample to sample, this estimated values, the sample mean or the sample proportion will change. So to overcome that problem, then we extend our point estimate as a confidence interval estimate. The confidence interval estimate also we estimate based on one sample, but there are range of values we are taking as an estimate, because there is a lower limit and the upper limit. Within that interval, infinite number of possible values are there for the estimates. So here for the variances or variability occurring due to sample is given, right? We are giving some concern related to the variability occurred from sample to sample. And also we are saying that to what extent our estimate is true. That means the population value will include the confidence interval, include the population value. So usually if we are taking the 95% level of confidence interval estimate, then we are saying that 95% of the confidence intervals constructed will include the true value of the population, and 5% of the intervals may exclude the true value of the population. Right? The true value is a parameter that is a constant that will not change, because for any one population, the parameter is a constant and that will not change. But when we are using the sample or statistic we are calculating, that will change from sample to sample. That's why we are taking the sample mean or sample proportion as a random variable, and then we are taking the constructing the probability distributions, right? This is the basic idea behind on the confidence intervals. Now we are ready to estimate the confidence intervals. So in the confidence intervals, we will learn about how we can construct for the confidence intervals for the population mean and for the population proportion, right? Under the population mean, there are two cases we will consider. When the population standard deviation is known, what is the confidence interval? And when the population standard deviation is unknown, what is the confidence interval? So the first case, we are going to construct a confidence interval for the population mean when the population standard deviation is known, right? So first, we will look at when the sigma is known, what are the assumptions, right? That is already we know that the population standard deviation sigma is known, and main assumption population is normally distributed. Whatever interval we are calculating, for most of the intervals estimation, the assumption population is normally distributed. If we don't know the population distribution, that is unknown or not normal, then we have to use the large sample. That means the sample size must be 30 or more than 30. Then, according to the central limit theorem, if the sample size is sufficiently large, then even the population is not normal, the sampling distribution has a normal distribution. With that assumption, we can estimate the population mean. So already we see that, yesterday we seen that the general formula of the confidence interval estimate is point estimate plus or minus critical value into the standard error. So according to this general formula, when we are estimating the confidence interval for population mean, our point estimate is always sample mean. So that is X bar. And if sigma is not, then here our critical value is the Z value. So we have to use the standard normal table. Right? So when we have to use this critical value as Z value, sigma is not. Then standard error for the sample mean is given by sigma over square root of n. So in this interval, this X bar we can estimate from the sample. This Z according to our level of confidence, then we can determine from the standard normal table. And sigma, this is population. Right? Then how we can find the critical value Z? Now, if we want to right, this 4:30 time only we are the last two classes we have the 4:30, right? Always you don't have the 4:30 power cut. It will change to places, right? So what are the thing we are saying in the class? You have to listen to that class, right? Then from the notes we are having with the clearly we are saying that. So there is no any recordings, right? If you want, you can record it, but I will not put the recordings, right? And also can't say that every 4:30 we are, the time is changing, right? This time also, if you have any 2 days 4:30 class, 4:30 power cut, then the time will be shifted. In such pattern, the power cuts are, they are implementing the power cuts. Not always you can't experience the power cut, right? The last week we have the 6:30 to 8:30. At that time, there is no any power cut, right? Okay. So what are the things we are saying? You have to listen to the class carefully, and what are the problems we are writing here, and we are explaining with the writing, that also you can note it. Right. Then this critical value, right? So how we can determine the critical value, right? So if we want to construct a 95% confidence interval, right? So this is our diagram. This diagram is for the standard normal, right? So now here I will explain how we can get the critical values, the corresponding critical values. Right. So this is a 95%. The whole shaded area is 95%. Then 5% will be allocated for the two tails, that is equally distributed, right? All together, under this bell-shaped curve, the total area is 100%. The total probability is 1, that is 100%. So when we are constructing a 95% confidence interval, this is the shaded area, right? 95% is the shaded area. Then 5% will be divided equally in the two tails. So if alpha, 1 minus alpha is 95%, then it is alpha by 2, then it is alpha by 2. Your alpha is 5%. right? Then alpha by 2 is 0.025, right? Then the rest of the half of the area is, if it is 0.025, then 5%. It is 0.5 minus 0.025, that is 0.475. Right? So now from this area, now if we get, this is our Z alpha by 2, right? We are marking this one as the critical table value Z alpha by 2. Right? So from this one, we can write probability of zero less than standard normal value, random variable Z alpha by 2 is 1.9, sorry, 0.475. This is equal to 0.475. Now this value we have to get the table, right? When you are searching this, where this 475 is located, according to the standard normal table, it will intersect, the point intersected where the row 1.9 and the column 0.06. So from this we can get that alpha by 2 is equal to 1.96, right? Because we know that from the table, probability of 0 less than Z less than 1.96 is equal to 0.475, right? So that is Z alpha by 2 is equal to 1.96. So by symmetrical, this value is minus 1.96, but only we need that Z alpha by 2. The magnitude of that value we need, that is 1.96. Right? Here this variable is Z. So from the table, even if it's a 90% confidence interval, right? Then this 90, for the 90%, if you want to calculate a 90% confidence interval, then it is Z. It is Z alpha by 2, and it is minus Z alpha by 2. This is 90%, right? It is 90%. Then for the tail, alpha is 10%. 1 minus alpha is 90%. From this, alpha is equal to 10%. So here the tail is 5%, that is 0.05, and this is 0.05. Then rest of the probability here, the shaded probability, half of the shaded probability, 0.45, I think. And from the table, where this 0.45 is located, that value you can get it from that table, right? As it is the previous chapters, I think when we are calculating the normal probabilities, we learned that if the probability is given, then how we can get the corresponding Z value. The same technique here also we have to apply, right? So the commonly used confidence levels are 90%, 95%, it is 99%. So if 1 minus alpha is 95%, then your alpha is 5%, right? If 1 minus alpha is 90%, then your alpha is 10%, right? If 1 minus alpha is 99%, then alpha is 1%. Right? From that, you can get the alpha by 2. And according to that alpha by 2, these are the some calculated values. You can check these values with the standard normal table. Then you can get the idea how we can get the corresponding Z value. Right? Then further explanations regarding the confidence intervals. This is our sampling distribution of the mean, right? So alpha 1 minus alpha percent confidence interval, this one. Then it is alpha by 2, general format, right? This is alpha by 2. This is here X bar, right? This is a sample mean in the horizontal axis. And this is the mu value, population mean, because always the mean sampling distribution mean is always equal to population mean. This mu should be estimated. So to estimate this mu, now here we are taking a sample, right? In this case, the first sample, this is X1 bar. Right? But this X1 bar falls within this interval. This is the lower limit of the interval, and this is the upper limit of the interval. Right? So now the X1 bar falls in this interval. So this X1 bar we can use as an estimate. When we are taking the second example, here this is X2 bar. This also include within this interval. Right? So this also we can use as an estimate. Similarly, there are, when we are taking each and every sample, you are getting the various values for the sample mean. Right? So if just we take a single sample, but we just be taking the one sample and only we are using the point estimate, then the variability will not be accommodated within that confidence interval, within that population mean, right? But when we are estimating this mu with a range of values, then this variability occurred due to the sample to sample will be included in the interval. But when we are looking at this interval, what will happen? This is now here. When we are connecting this line from here, this is beyond the lower limit. This value, this mean value is beyond the lower limit of the confidence interval, 1 minus alpha percentage confidence interval. But in this case, it's excluded the mean value. So that also will be accounted by the, because we are giving 5% uncertainty. That means 5% of the intervals exclude the true population value. So 95% confidence interval means, or 1 minus alpha. If we generalize general form, when we are taking one minus alpha percentage mean, right? 1 minus alpha percentage of the confidence interval contain mu. That will include the true mean value, that is population mean value. But alpha into 100% do not include the mean value. So if you are taking 95% confidence interval, then 95% of the confidence intervals include the mean value, but 5% of the confidence interval exclude the mean value. This is one of the example. This interval coming under the 5% levels of the intervals, right? Here it is exclude the population mean, but all other intervals includes the population mean. This is the basic general explanation of the confidence interval for the mean value, right? Now we are taking a simple example how we can calculate the confidence interval. Here it is regarding the demand for the computers, right? The samples, we are taking the samples and we are looking at the demand of the computers during the lead time over 25 time periods. Right? That means 25 time points we are taking, and these 25 time points are the lead times. So during the lead times, how many computers are demanded? Right? So the first time point, there are 235 computers during the lead time, then 374, like here, these are the number of computers demanded. And also, another information they gave, it's known that standard deviation of demand over lead time is 75 computers. This is regarding the population value, right? This will not related to the sample information, right? So it is known that standard deviation of demand over lead time is 75 computers. Assume that the number of computers over lead time is normally distributed. Already they have that. It is a normally distributed. So now estimate the mean demand over lead time with 95% confidence. Estimate the mean demand, right? Over lead time with 95% confidence in order to set inventory levels. Right now, we take our random variable related to this problem. X is number of computers demanded during the lead time, right? Number of computers demanded during lead time. And X bar, mean number of computers demanded. Then this X bar, how we can calculate this X bar? Here we know that for 25 time periods you have the computer. So X bar is equal to, you have to use your calculators, then you can get the value. X bar is equal to 235 plus 374. Similarly, all the 25 periods time points you have to add 334. Then there are 25 periods this was observed, then divided by 25. From this you can get the value X bar, right? And also they say that this time is normally distributed, right? X has a normal distribution. From this we have X normally distributed. This mean value is we have to estimate unknown, comma, your standard deviation is 75. That is sigma is equal to 75. And n is equal to 95. These are the information we have. This is unknown. This value should be estimated. Right? So the point estimate is what is the mean value you got by calculating this sample mean, that will be the point estimate. But here we have to find the 95% confidence interval, right? So here this population standard deviation is not. So your confidence interval is calculated by 95%. Confidence interval is calculated by X bar, point estimate, plus or minus your critical value. Right here. 95% confidence interval. Point estimate, general formula, plus or minus critical value. So here sigma is not, your critical value is Z or Z alpha by, right? Both notations, either one of the notation you can use, Z or Z alpha by 2 into standard error. It's related to X bar. So the standard error is sigma over square root of n. Right? This is the formula we have to apply. This X bar we can get from the sample mean, then Z alpha 95%, 1 minus alpha. So here alpha by 2 is 0.05, 0.025. So from the table, Z alpha by 2 is equal to 1.96. Then your sigma is 75 and n is equal to square root of 25. That is 75 over 5. Right. The next slide, you have the answers. Right. So here X bar calculated 370.16. You can check with your answer. Right. So that is X bar is equal to, we apply the formula, summation I is equal to 1 to n 25 xi divided by 25. Then 95% confidence interval. So 1 minus alpha is 0.95. Therefore, alpha by 2 is 0.05. This is from Z alpha by 2. That is from the standard normal table. And also sigma was given, that is 75, population standard deviation, and n is the sample size 25, that also given, right? Therefore, this is the confidence interval when sigma is known, population standard deviation is known, that is 370.16 plus or minus Z alpha by 2, right? Into sigma 75 n root of 25. That is 370.16 plus or minus. From the table, this is 1.96. That is actually probability. This value is you can get by probability of 0 less than Z alpha by 2 is equal to 0.475. This Z alpha by 2 equals 1.96. Right? So when we are simplifying this figure, then you will get 370.16 plus or minus 29.40. Right? Then to get the lower limit, first when you are specifying the confidence interval, the first value you have to specify the lower limit. So how you can get the lower limit? This is 370.16. This is equal to 370.16 minus 29.40. This is your lower value. Then the upper value, 370.16 plus 29.40. This one results 340.76 and you added with 29.40, that is 390.96. lower limit of the confidence interval. This is the upper limit of the confidence interval. Then actually what is the meaning of this interval? The mu will be in between your population mean, right? Or the population mean of computers demanded during the lead time, right? The population mean of the computers demanded during the lead time is 340.76 in between and 390.56. Right? So only here you have to find the mean value that will be get from your sample observation, and this one you can get from the table, and these two things you get from the given problem. Right? So now the interpretation, how we can interpret that also you have to know that, right? How we have to interpret. So we are the 95% confidence interval, how we can interpret? We are 95% confident that the population mean demand of computers. Always you have to relate with the given scenario, right? So here we calculate the mean, estimate the mean value for the demand of computers during the lead time. That should be specified when you are making the interpretation. So the population mean demand of computers during the lead time is between 340.76 and 390.56. That means here actually this is 340.76 less than or equal or less than mu less than 399.56. So one of the value within this range of the values or within this interval, one of the value will be the true mean value, that is population mean of computer demand. Right? But what is your sample mean value? X bar, that is 37.16. So X bar is equal to where? 37.16. This is our point estimate. And this is the interval estimate, right? So now you see this 370.16 also including within this interval. So the population mean will be between 304.76 and 399.56. Right? So in such manner, you have to write the interpretation. So this is for one example here we interpreted. So the similar pattern you can follow to make the interpretation. But when you are interpreting the confidence interval, the scenario should be related. So here the mean for the demand of computers during lead time. This is the problem. Attend this information, true mean may or may not be in this interval, right? It may or may not be. So the now only 95% intervals formed this manner will contain the true mean, but 5% will exclude the true mean, right? Only 95% include this true mean, but 5% exclude the true mean, right? Here, 5% will exclude the mean. So this means your 5% will exclude the true mean, right? Now another example we are taking. Here we are taking 11 circuits, right? A sample of 11 circuits from a large normal population. Here also we have a population is specified as normal, has a mean of resistance 2.20 ohms. It's a measure, a unit of measuring the resistance, we are using the ohm value. You learn this one about in your O-level physics, right? How we are measuring the resistance using the ohm value. So here the mean value is given. So from this, if n is equal to 11, now we are taking, it's measuring the resistance of a circuit, right? So X is the resistance of a circuit. It's related to electricity problem. Then they have X as a normal distribution. X follow normal distribution. Here we have to true mean resistance. This should be estimated. Mean resistance that is unknown. So we comma standard deviation. We know from the past testing that standard deviation is 0.35. So we have sigma is equal to 0.35. So that is 0.35. And X bar is a sample of 11 circuits from a large normal population has a mean resistance of 2.20. So their X bar is equal to 2.20. Right? And also we have to determine 95% confidence interval. So 1 minus alpha is 95%, that is 0.9. So from this, we have alpha by 2 is 0.05 divided by 2, that is 0.025, right? From this standard normal table, Z alpha by 2 is 1.96. Now, what is the estimate? Confidence interval estimate we have to find. Estimate of V. Right? So here there is no need of calculating the sample mean. Already they gave the problem. It is just we have to find the confidence interval, right? Now all the things we know that. So point estimate of mu is from the given scenario. So X bar is, now here we can denote X bar mean resistance. Mean resistance of 11 circuits. Mean resistance of 11 circuits, right? So the point estimate is of mu is X bar, that is equal to 2.2. This is our point estimate. Now we have to find what is 95% confidence interval estimate. That is equal to X bar plus or minus critical value Z alpha by 2 into standard error sigma over square root of n. Right? So X bar from the given situation, X bar is 2.20 plus or minus Z alpha by 2, 1.96 into standard deviation is given as 0.35. The sample size is 11 circuits they considered. That is, by simplifying this, given this expression, then you can get the lower limit and the upper limit of the 95% confidence interval. Then answer for this one. Right? So here x bar is z plus or minus z or z. The z you can use z or z alpha by both notations. Either one of the notation you can use. Then x bar is 2.20, 1.96. So that is 2.0 plus or minus 0.2068. So then this is the lower limit. This value is this is equal to 2.20 minus 0.2068. Always the first value will be the lower limit, that is the minus sign, and your upper limit you can get with the 2.20 plus 0.20. By simplifying this one, then you will get, right? So here this means the mean of resistance, right? The mean of resistance for the circuits will be between 9.932 and 2.406. This is with the 95% confidence, right? So how we are interpreting that? We are 95% confident that the true mean resistance, right? Here we are estimating the mean value for the resistance. So this true mean resistance is between what value is, right? All. Further, the true mean may or may not be in this interval, but 95% of the intervals formed in this manner will contain the true mean, but 5% will exclude the mean, right? Now here exercise. I will make the explanation here. Then you have to complete this exercise. Right. So a paper manufacturer has a production process that operates continuously throughout an entire production shift. The paper is to have a mean length. It is expected, right? The paper is expected to have a mean length. And the standard deviation of length is 0.0. These both informations are related to population, right? Here we don't have any information regarding sample, right? So the expected mean is for a paper length. Expected mean mean of length paper, mean of length of paper mu is expected approximately 11 inches. And also they gave that sigma is 0.02. Right? At periodic intervals, a sample is selected to determine whether the mean paper length is still equal to 11 inches. They want to test or they want to check whether still mu is 11. They want to test whether mu equals 11. Something if it's not equivalent, then the production process is something wrong, right? So to check whether this mean length is 11, they select a random sample of 100 sheets. They select a random sample of 100 paper sheets. N is equal to 100. And the mean paper length is 10.998 inches. Now say that this is X bar. X bar is 10.998 inches. Right? So now construct a 99% confidence interval estimate for the population mean paper length. Right? So now we will look at, so our random, regarding this given scenario, now we can take X as a length of paper and X bar mean length of paper. What is the distribution of X bar? The population distribution now, X. There is no any information of X. The distribution of X is unknown. Right? But N, the sample size is greater than 30, but X bar has a normal. Why? Because N greater than or equal to 30. Right? So according to central limit theorem, we can say that. Also, we can get the information from this one. Right. So now the 90, what is our confidence interval? 99% confidence interval, right? So 1 minus alpha is 99%. Then from this alpha is, I think, 1%. That is 0.01. Right? So from this, your alpha by 2, 0.05. From this, I think that alpha by 2, 0.58, I think. You check with the table, it is 2.58 or 2.57, right? So your 99% confidence interval now is given by it is related to sample mean, so X bar plus or minus Z alpha by 2. Our sigma is not sigma over square root of N. Right? Then X bar, given that 10.998, Z alpha by 2, 2.58 into sigma, here it is population standard deviation. from the first statement, you can take 0.02 and in from your sample size, 11 sheets was taken. That is square root of 1. Right? By simplifying this one, then you can get the confidence interval. And also, based on the previous slides, how we make the interpretation, in similar pattern, you can also make the interpretation. Then whether the production process is working properly, justify your answer. Right? So how you are going to justify your answer, whether the production process is working, our mean value is expected here 11. Right? This mean value is expected 11. Right? So this interval includes this 11. Right? If your confidence interval includes this 11, then we can say that the production process is working. Right? You can say that because this interval includes the expected mean value 11, then we can conclude that the production process is working properly. Suppose this interval does not include the value 11. Right? The interval does not include the value 11, then you can say that the process is not working. Right? How you can get the answer, check this answer whether the production process is working properly. Check whether 11 is included within this interval or not. If 11 is included in this interval, then you can say that the production process is working properly. If this interval excludes 11, then you can say that the process is not working properly. Right? So if you want this points, then you can note it. Then I'm going to move for the next slide. Right. So now we are moving to the next part of confidence intervals. So far, we learned how we can calculate the confidence interval for the population mean when sigma is known. Right? When sigma is known, how we can calculate the confidence interval. If the population standard deviation is unknown, then how we can calculate the confidence interval, right? So if the population standard deviation is unknown, then this sigma we have to estimate using the sample information. This population standard deviation should be estimated the sample standard deviation, right? For sample standard deviation, the formula how we can estimate this one, S is equal to 1 over n minus 1 summation of xi minus x bar holding square. This is in the chapter 2 or 3 we learned, right? Under the status numerical measures, we learned how we can calculate the standard deviation for the group data and for the ungrouped data. If you have an ungrouped data, then this is the formula we have to use to calculate the standard deviation. So the sigma will be replaced by the sample standard deviation, which is calculated by using this formula. But here, this also will change sample to sample. For when we are taking the different samples, this one S also will be get different values. So here the extra uncertainty for like the mean value for this also we are taking the extra uncertainty. Right. So here the two cases extra uncertainty value and for the standard deviation, because two parameters are estimated using the sample information. So in that case, we are using the T distribution, right? Because T distribution is the robust distribution instead of using the standard normal, right? So we have to use the T distribution for the when the assumptions are violating. This also to some extent the violations will be taken into the consideration when we are using the T distribution. That's why we are saying that this is the robust distribution. The T distribution is robust. So because here two parameters we are estimating using the sample information. So the assumptions violations of the assumptions are possible. So to avoid those uncertainty occur, then we are using the T distribution instead of the normal distribution. This T distribution is also like a symmetrical bell-shaped curve, right? It is symmetrical around like a standard around 0 value. But the tilts are curve than the normal distribution. Suppose if this is the standard normal, this is Z for a particular N, it is 0, but your T distribution, right? T 0. These tails, both tails are thicker than the tails in the standard normal distribution, right? That both tails of the T distribution are thicker than the standard normal distribution tails. This is the difference between the T distribution and the normal distribution. So comparing to this standard normal, more observations are coming with the tails, falling under the tails, comparing to the standard normal, right? But both are bell-shaped symmetrical around the 0, right? That is the only difference between the confidence interval when we are taking the standard deviation is known and the standard deviation is unknown, right? So assumptions as it is in the previous, when sigma is known, the population also normally distributed. If the population is not normal, we have to use the large sample. But in this case, standard deviation is unknown. So we have to use the student's T distribution instead of standard normal distribution. Then in the confidence interval estimate is given by x bar plus or minus t n minus 1. Now the critical value z is replaced by t n minus 1 into s over square root of n. The previous one, when sigma is known, if sigma is known, then confidence interval is x bar plus or minus z into sigma over square root of n. Right? Now x bar is same. When sigma is unknown, x bar is same. That z now is replaced by t with n minus 1 and sigma, which is replaced by s square root of n. So now the standard error is also estimated with s over square root of n. N minus 1 is the degrees of freedom. N minus 1 is called the degrees of freedom. With the t distribution, to get the critical value for the t distribution, we have to know the degrees of freedom also. The t distribution is depending on the degrees of freedom. So when the degrees of freedom are increasing, that means for the large samples, the t distribution is approximately close to the normal distribution. Right? So now, what is this degrees of freedom? So t distribution is like a normal distribution. The t distribution is also a family of distributions. When the value of n changes, the shape of the distribution also, that means the thicker tails becoming very thin tails when increasing. N is increasing, the thickness of the tails becoming thin. Right? And also, if we are simply interpreting the degrees of freedom, they are free to vary. How many observations, right? How many observations are free to vary after sample mean has been calculated? Now suppose example, we have observations, three observations, 1, 2. This is x. And your sample mean x bar is 2. X bar is equal to 2. Now from this information, we can find out, now say that y. What is the value of y? We can say that, right? So now y is equal to, x bar is equal to 1 plus 2 plus y divided by 3. From this, 3 plus y is equal to 6. From this, y is equal to 6 minus 3, that is equal to 3. So the value of y is depending on these two values. The value of y is depending on these two values. So now this y is not free to change after sample mean has calculated. Mean is not, then the y does not vary. That this value is decided by based on these two values. But now these two values we can change. Now we say that this is 0 and 2, comma y. And your x bar is equal to 2. Now this y is again depending on these two values. Right? So these two values we can change. But if we change these two values, then after calculating the mean, this y is depending on these two values. So only if there is n observations are there, n minus 1 observations can. Now here 3 observations are there, 2 observations are free to change and 1 observation does not free to change. after creating the mean value. So similarly, if there are n observations, then n minus 1 observations are free to change after calculating the mean value. That is given by degrees of freedom. Right? So the same examples here we looked at. Now the distribution, when n is very big, always it is same as the standard normal distribution. With 0, it is becoming z when n is very, very large. That means t tends to z as n increases. Now we're looking at degrees of freedom, the tails. Right? Here it is more thicker comparing to this one, and also the ranges also will become smaller. More fat in the tail for the less n values, right? N values are increasing, then degrees of freedom also increases, because degrees of freedom is n minus 1. So if the n values are increasing, then degrees of freedom also will increase, and also the tails will become skin, and also the length also becoming small, and it is very close to standard normal distribution. Right? Now you take the standard normal, table. You have a T table, right? That was uploaded in the LMS. Now, if you want to look at in the T table, in the body, they don't have the area. But in the standard normal table, the body includes the probability values area. But in the T table, that will not area is into critical step. So in the first column shows the degrees of freedom, and the very first row includes the tail areas. Right? Now we have a degrees of freedom 2, that is n minus 1 is 2, and your upper tail area is 0.05, then the corresponding t value is 2.920. Now you take the table. Right? So here this is alpha. If your right tail, right? One of the tail is alpha, then these are the alpha values. And here this is the degrees of freedom. Right? Now say that if your confidence interval, we want to calculate the 95% confidence interval, right? We want to calculate the 95% confidence interval. Then 1 minus alpha is 95%. Then this alpha is, then 2 tail will be 5%, and then your alpha by 2 is 0.025. Right? Alpha by 2 is, for the 95%, this value will be 0.025 for a 95% confidence interval. Then your degrees of freedom, suppose there are sample sizes n, that is 7, n is equal to 7, then the degrees of freedom is 6, and then 2.447. Right? Similarly, you can use this student T distribution to get the critical values, right? Right. So now from the table, by using the table, you can check the confidence level is 0.80, that is here, if 1 minus alpha for this case, this is 1 minus alpha, 80%. So from this, your alpha is 20%. Alpha by 2 is 10%. That is 0.1. Then you take the table and check. When degrees of freedom is 10, with your alpha is 0.1, what is the t-value? When the degrees of freedom is 20 and alpha is 0.1, what is the t-value? When degrees of freedom is 30 and alpha is 0.1, then what is the t-value? Right? From the table you can get. Right? And also if we look at when for the 80% confidence, if the Z value is 1.28. Right? So now you see that when the degrees of freedom is increases, that means in this increase, Z value is becoming close to Z value, right? So it is 1.37, it is 1.32, it is 1.31. So this is 1.31 is more close to 1.28 comparing these two values. Similarly, here it is a 90%. So here alpha is 10%. Then alpha by 2 is 5%. That is 0.05. Right? Like a table here, this is the table. Right? For the first case, this is 80% for the first case, right? And it is 10%. And this is 10%. Right? And for the second case, is T, right? 90%. So this is 5% and this is 5%. Similarly, you can share the tail probabilities by looking at those confidence levels, right? Right. Here, a small example here we take a random sample of n is equal to 25. We take from a normal population. We take from a normal population. And we say that X bar is equal to 50 and S 8. So these two values are estimated from the sample, right? X bar is 50 and the sample standard deviation usually denoted by sample value. Both are estimated from the sample of size 25. Then you have to form a 95% confidence interval. So in this case, sigma is unknown. So if the sigma standard deviation is population standard deviation is unknown, then 9 confidence interval is given by X bar plus or minus T alpha by 2 comma n minus 1, right? So in this case 95%, so 1 minus alpha is 95%. So alpha is 5%, that is 0.05. Alpha by 2 is equal to 0.05. And the degrees of freedom is n minus 1. Your n is 25. 25 minus 1, that is 20. So if we take the diagram, this is 0.025. So this t value we have to calculate, find out, right? T with the tail, right tail is 0.025 with your degrees of freedom, 24. Now you take the table 0.025 with 24. 0. This tail, this probability is 0.025, right? This one. And of is 24. This is 24. The intersect point is 2.492. Check with this value. 0.025. Sorry. This one. This is right. 0.025, third column, right? Third column with 24. 2.064. 2.06. When for the third decimal, when we are adjusting, 2.064. Right? So now this is the confidence interval. So x bar is equal to what is 20, where 50. And between 46.69, right? Now you think about this problem. Calculate the mean values and the standard deviation. In another 5 minutes time, I'm giving to you, right? Then calculate using the calculators. Right here, I'm giving the instructions how you have to do this one. Then complete this one as a homework. Right. This is a manufacturing company. It produces electric insulators. Right. Then if the insulators break in use, a short circuit is likely. Right. So to test the strength of the insulators, they want to measure the strength of the insulators. The destructive testing was carried out and was determined how much force is required to break the insulators. Right? So the force was measured are applied to the insulator before it breaks. So here we are measuring the force. This force was measured by the pounds, like a kilograms, right? So 30 insulators was taken, sample that is a destructive, for this experiment listed below. So on the N is equal to 30, and from these 30 insulators, what are the forces they implemented before breaking the insulator, right? So now construct a 95% confidence interval for the population mean force, right? For the population mean force required to break the, right? So now here, first you define X. What is X? That is force required to break. That is measured in the pounds. Required to break. No, X has, the distribution of X is unknown, right? The distribution of X is, there is no any information regarding the distribution of X. So the distribution of X is unknown. So here, from this mu also unknown. Estimated, right? Here they are asking 95% confidence interval, and the standard deviation sigma is also unknown. Then X bar, we can say that that is a mean force required, right? X bar is a mean, not force required, or average force required to break. And therefore that they take, for this estimation, they take 30 population, 30 sample values, right? In this. So now we have to take 95% confidence. Right? So the 95% confidence interval is given by here. X bar, because sigma is unknown, right? So we have to use the T distribution. T alpha by 2 minus 1 into sigma over square root of n, that is S over square root of n, right? Then X bar, you can calculate from this figure. So X bar is equal to 1870 plus 1728. Similarly, you have to add all these values. 6 divided by how many observations we got? 30 observations. Right? Then S. So S is equal to, S squared is equal to 1 over n minus 1 summation of I is equal to 1 to n xi minus x bar, where that is equal to, rather than taking this formula, this is always equal to calculated formula, square root of one over n is 30. So 30 minus 1 into summation of I is equal to 1 to n xi square, right? So each and every value should be squared and added, minus summation of I is equal to 1 to n xi divided by n. Right? By using this formula, you can get the S value. Right? And then for the T value, critical value from the T distribution, 1 minus alpha is 95%. So alpha is 0.5. Then alpha by 2 is 0.025. You have to get the critical value T 0.025, n is 30 minus 1, 29 from the table, right? After finding all these values, then by using this formula, when you are substituting on this, then you can get the 95% confidence interval. And also, you have to how you can interpret it, right? So, complete this homework. So, now the confidence intervals we calculated for population mean. So, to estimate the confidence interval for the population mean, there are two cases we learned. One is sigma known and sigma is unknown. If sigma is known, then you have table. Here we are using the Z standard normal table, critical value. And if sigma is unknown, then we have to use critical value as from the T distribution. To decide the critical value, this n minus 1 also need, that is called as a degrees of freedom. Right? So now we are coming for the population proportion. The next confidence interval, population proportion. Right? Right. So here the population proportion, we are denoting the population proportion as pi. For the population mean, we use the notation mu, but here we are using the population proportion pi, right? So the sample proportion is denoted by small p. This percent point estimate of pi. Then how we can calculate this p? These are the, yesterday also we see this formula, right? X, that is number of items in the sample having the characteristic of interest divided by n, that is the total sample size. Always the proportion in between 0 to 1. Usually this is a binomial distribution, but when n is very large, the sampling distribution is has a approximately normal distribution, right? This is from a finite population with replacement or without replacement from the infinite population, right? Then this is also be seen in the sampling distribution, right? So always the population proportion is approximated by a normal distribution. With the mean is population proportion pi, and Standard error or standard deviation is given by pi into 1 minus pi over n. But actually, when it has a normal approximation, n into p greater than or equal to 5 and n into 1 minus p greater than or the two conditions. To use normal distribution, these two conditions we have to check. N is the sample size, p is the sample proportion. So multiplication of these two figures should be greater than or equal to 5. Then an interval estimate for the population proportion pi can be calculated by adapting an allowance for the uncertainty to the sample proportion. The same thing, right? Our general formula is for the confidence interval. So for 1 minus alpha 95, 1 minus alpha percent confidence interval is point estimate plus or minus critical value into standard error. So here the point estimate is plus or minus the critical value as it's a normal distribution Z. We have to get from the Z table. And the standard error is here your standard error is this one, but this is replaced by p-value because this is population proportion is unknown. So to estimate the population proportion, this is p into 1 minus p over n. Right? Sorry for the disturbance. Right. So based on this general formula, now here this P is a sample proportion. That's P you can calculate from X over N. Right? X is the number of the attributes which are interested. Right? So the distribution of proportion is approximately normal if the sample size is large. Then the deviation, sigma p, that is pi into 1 minus pi over n. So when we are, if the this is unknown, distribution proportion is unknown. So this should be estimated with the sample data. Here we are seeing p into 1 minus p over n. Right? Because we want to estimate as a confidence interval, we want to estimate this one. So Now this should be estimated with sample proportion. So this is final your confidence interval endpoint. P is equal to P plus or minus P equals P into 1 minus P over A. Then now here a very simple example we are 100 people shows that 25 are left-handed. Right? So form a 95% confidence interval for the true proportion of left-handers. Right? So now P, we are taking pi. We are taking pi is a true proportion of left population or true proportion of left hand. Then the P is equal to sample proportion. Equal to sample proportion of left-handers. Right? And that is given by there are 100. 25 are left-handed. So 25 over 100. X over N, right? P is equal to X over N. That is equal to 25 over 100. That is 0.5. Right? And also you can check that whether we can use the normal distribution to check the normal distribution. Check whether P has a normal distribution. We have NP, that is N is 25 into 0.25, that is 6.25 greater than 5. 1 minus P also, that is 25 into 1 minus P, 0.75. I think this also greater than or equal to 5, right? NP and NP minus 1 minus P greater than or equal to 5. This also greater than or equal to 5. So we can have a confidence interval, then 95% confidence interval for, so the point estimate of pi, right? The point estimate for pi is point estimate pi is equal to P, that is equal to, then confidence interval estimate for pi is this is confidence interval, right? So pi P plus or minus Z. Here alpha is 95%, 0.025 into P into 1 minus P over N. So that is equal to P. Then plus or minus P is 0.25. And this Z value from the standard normal table 1.96 into P is 0.25 into 0.75 divided by N is equal to 100. Right? So by simplifying, by simplifying this interval, then you can this expression then you can get the confidence interval, right? Anyway, answer is provided here. Right? So the left-handers proportion, true proportion of the left-handers, we are 95% confident that based on this one, we are 95% confident that the true proportion of left-handers is between 0.1651 and 0.3349. That is 60.5% and 33.49%. Then interpretation, we are 95% confident because 95% confidence interval. So we are 95% confident that the true percentage, if we are giving the proportion, true proportion, then 0.1651 and 0.3349. Here we are taking the true percentage of left-handers. The proportion is between 16.51% and 33.49%. If you are putting the proportion, then this will be 0.1651 and 0.3349. Although the interval from this one may take true proportion, 95% of the intervals form such intervals will include the true proportion, but 5% excludes the proportion, right? And this exercise, I will explain this one, then you complete as a homework. Here, this operation manager at a large newspaper wants to estimate the proportion of newspapers printed that have a non-conforming attribute. This is one type of attribute regarding the newses, right? Conform news and non-conform news. So non-conforming attribute and conform that, non-conforming and conforming, right? Such as excessive rub-off, improper page setup, missing pages. Right. So here the non-conforming attributes means how they are describing, that is the errors. That non-conforming attributes are the errors, excessive rub-off, improper page setup, missing pages or duplicate pages. These are saying that non-conforming. So to identify, to estimate the proportion of non-conforming attributes, they select 200 newspapers is selected from all the newspapers printed during a single day. Right? In this sample, 35 contain the type of non-conformance. Construct and interpret the 90% confidence interval. So now we are saying that is the population proportion of non-conforming or non-conformance. Then P, the sample proportion of non-conformance. And from the given example, the P is equal to 35 over 2. Then you can put in the decimal points, right? And also check whether NP greater than or equal to 5 and then P into 1 minus P greater than 5. You have to check this, right? Where N is equal to 200. And P you can get from this value. You can then 90% confidence interval you have to construct. And then the point estimate for the non-conformance is 35 over 200. Right? The point estimate of the non-conformance is 35 over 200. And the 90% confidence estimate P plus or minus Z, 10% for the two tail, so 5% for the one tail, so the critical value 0.05 you have to get from the table into P into 1 minus P. If P from this you can get, and N this is 200, and 90% is with the tail 0.05 from the standard normal table, you can get this, right? And finally, you can get the proportion. So, the determining the sample size, we have to get tomorrow we will learn. Tomorrow also you have the lectures, right? This one, and we will start the hypothesis testing. So tomorrow, whether you want to have the lectures time 7 to 9 or 4:30 to 6:30. Now you decide the time. Now, once the student compliant, he or she is suffering from the power cut. So now you decide whether you want to the lectures 7 to 9 or 4:30 to 6:30.
Seven to 9, ma'am.
7 to 9, right?